section 4.7, change of bases. So sometimes you have a way to change from one base to another base, and the idea behind changes to another base is to make things easier for later on. So that's what this section talks about. How do we change from one base to another base? And to do so is we take a vector x in the vector space V. Okay, we need to see how the components, so the bracket means components here, the components, so sub B, this means components of the vector x in the basis B. Okay, in the basis B, so B is the basis. So we're gonna see how the components of the basis B or C and that of the same components of x in base B are related for each vector x in the vector space V. That's what we're going to be seeing. Let's say we're working in two-dimensional space, and say if x is given as in terms of the B's 3b1 plus b2 and vector x 6c1 plus 4c2, then x in the basis B is given by, is basically we take the coefficients of the B1 and B2, which is 3 and 1. That's for the B, so 3 goes here, 1 goes there. And the components of x in the basis C, again you take the coefficients 6 and 4. 6 and 4. So let's say now as an example, another example, say B has the vectors B1, B2 and C, C1, C2 in the vector space V, where B's, the B1, B2, C1, C2 are related with these equations. B1 is 4C1 plus C2, and let's say B2 is negative C1 plus C2. Also, let x 3b1 plus b2, the vector. So this means x in the basis B is 3, 1. And what we need to find the components of the vector x in the basis C based on the given information. So how do we start with this one? We want to find the components of x in base C. That's what we need. We can write it as, what is x? X is given as 3b1 plus b2 in the basis C. Then you can split this into 3b1 in the basis C plus b2 in the basis C. And what we just wrote here, okay, what we just wrote, we can rewrite this as a matrix. How do you write that as a matrix? We take those B1C and B2C and multiply all this by these coefficients 3 and 1, 3 and 1. Right? Rewrite it this way as a matrix. What is B1? B1 is 4C1 plus C2, right? Up here. So we can write it. So 4, 1. And B2 is given negative 6C1 and C2. And we're going to multiply this by 3, 1. How do you multiply matrices? Row by column, right? Row by column. Let's see what we get. 4 times 3, 12, plus negative 6 by 1, negative 6. So that's a 6. this times this, 1 times 3, 3 plus 1 times 1, 1, so 3 plus 1 is 4. So that gives us exactly the coordinates or the components of C of X in the basis C. Now we can introduce a theorem. So the theorem said if we have two bases, B with the vectors B1 all the way to Bn, and C with the C1 all the way to Cn, be bases of V, of the vector space V, then the theorem said there is a n by n matrix, so it's a square matrix, P, that transformed the base B to base C such that the components of X in the base C is basically given by this matrix. This is a matrix that takes B to C times the components of X in the base B. So what is this here? This contains, its columns are basically the C coordinates or the C coordinate vectors of the coordinate vectors of the vectors in basis B. Okay, so here is, what does this mean here? So if we go from B to C, so we do the vectors of B1 with respect to C, vectors B2 with respect to C, and it goes all the way to BNC. So these vectors are linearly independent. So if you go from B to C, as you can see here, we have outside. So whatever you have here, it goes out. If it goes from C to B, then B goes outside. Just keep that in mind. Sometimes students switch them out. Also, from what we wrote earlier, XC, we wrote it this way. So this matrix is a square matrix, n by n. It's an invertible matrix. So what we can do, because it's invertible, we can multiply both sides by the inverse. With this. Oops, I forgot the one next to it. The matrix here, B from B to C times X in the basis B. This one is the identity matrix, it's gone. So that gives us B to C, the inverse, times X in the basis C is X in the basis B. So we can conclude that the inverse from B to C is the same as from C to B. So this helps with calculations, and we'll show you examples on this. Now, if bases B, again, call them B1, B2, and C, C1, C2, are given. How to find the question we need to answer now? How to find the change of coordinates? How to find the change of coordinates matrix from B to C? If you can do from B to C, we can easily go from C to B. Now, B1 in the basis C, say has x1, x2, and B2 in the basis C with components y1, y2. Now, by definition, if we take C1, C2 and multiply them by x1, x2, that would give us B1. And if we take C1, C2, multiply by y1, y2, that would give us B2. So remember here we're going from B to C. So if we're going from B to C, we start with C1, C2, B1, B2. And we're gonna do some row operations on this to rewrite it as the identity matrix. And whatever we get here, we get the matrix that we need that gives us the change of the bases from base B to base C. So keep in mind, if you're going from B to C, so going from B to C, then C must go first in here. If you go from C to B, then you put the B's first. Kind of like backwards. With the example, things will become easy. Say B1 is this, B2 is given 1, -5. C1 equals 1, 4. C2 equals 1, 1. And consider bases for R2 given by B equals B1, B2, and C equals C1, C2. Find the change of coordinates matrix from B to C. So remember, we're going from B to C, B to C. So what do? Because B to C, we start with the C's, C1, C2, B1, B2. C1, 1, 4, C2, 1, 1, negative 1, 8, 1, negative 5. And remember what we need to do with this matrix. I want to get the identity matrix there by performing some row operations on this. So what am I going to do here? We are going to take, I already have one there. I'm going to take negative 4R1, add it to row 2. Let's see what we get. 1, 1, negative 1, 1. That's a 0. Negative 3. That's a 4 plus that, 12. Negative 9. Right? So I cleaned the first column. Then I'm going to make this number negative 3 to become 1. So negative 3, 1/3, row 2. 1, 0, 1, 1, negative 1, 1, negative 4, 3. So now I take that one and I use it to clean the number right above it. Negative row 2 added to row 1. So we get 1, 0, 0, 1. 4 minus 1 is 3. And this is negative 2. Stays the same. So now from here, this is our identity matrix, and this is the P that transforms B to C. So we get that from B to C is 3, negative 4, negative 4, 3. Which we can write it if you like. B1 to C, B2C. Any questions up to this point? Now, let's take the same question. How about, for the same problem, how about finding the change of coordinates matrix from C to B. We did B to C and now C to B. And to do so, we're going to use the breakout rooms. So now we're going from C to B. So we put the B's first, B1, B2, then C1, C2. This gives me negative 1, 8, negative 1, negative 5. 1, negative 5. 1, 4, 1, 1. So first thing I do, I'm gonna multiply. I want to make the first number 1, not negative 1. So multiply row 1 by negative. So that gives us 1, 8, negative 1, negative 5, negative 1, 4, negative 1, 1. Now I want to clean up the first column. We multiply the first row by negative 8 and add it to row 2 to clean up the first column. So that gives me 1, 0, negative 1, a 3, negative 1, 12, negative 1, 9. Now I want to make that 3, 1, so I do 1/3 row 2. 1, 0, negative 1, 1, negative 1, 4, negative 1, 3. Now I use this one to clean up that column. So I do row 2 added to row 1. That will clean it up. Oops, added to row 1. So it's 1, 0, 0, 1. negative, actually 3, 4. So this part here is what we're looking for from C to B. Remember, recall, we proved earlier that if you want to go from C to B, what you can do, you can take B to C and find the inverse. Remember? That's just another way to calculate this. Now, so I'm gonna use this as a second method now. So we write B from C to B equals the inverse, B to C inverse. And what was the one we found earlier? 3, negative 2, negative 4, 3. And we need to find the inverse of this. So this was the first part of the previous problem. We got 3, negative 4, negative 2, and negative 3 for the matrix from B, coordinates from B to C. So what I'm gonna do here is we're gonna find the inverse of this. How do you find the inverse of a 2 by 2 matrix? If you remember, if you have a B, C, D, the inverse is 1 over its determinant times you swap A and D and change the signs of B and C. So it's going to be 1 over 3 times 3, 9, minus 8. And we swap 3 and 3 and switch the signs. So that gives us 1 over 1, which is 3, 4, 2, 3. And if you look at this answer, I got 3, 4, 2, 3 is the same as this one, 3, 4, 2, 3. One thing we have to be careful about this method. I know it's a really quick as a shortcut, but if in case you get this wrong, the first part wrong, then the second part automatically will be wrong. Like the answer will not match, let's say, the back of the book. That's the only difference. Let's look at a different example. Let D be D1, D2, D3. F is given F1, F2, F3B, 2 bases. For a vector space V. And suppose F1 equals 2D1 minus D2 plus D3. F2 is 3D2 plus D3. F3, it's negative 3D1 plus 2D3. Part A, find the change. Find the change of coordinates matrix from F to D. And part B, we're gonna find the components of X in the basis D for X to be given as F1 minus 2F2 plus 2F3. So for part A, we need to find the matrix D, coordinate change of coordinates from F to D. So how do you do this? We need to find F1 in the basis D, F2 in the basis D, F3 in the basis D. And to do that, so if we go back up here, f1 in the basis d, it's the coefficients 2, -1, and 1. And we do the same thing for this one. f2 in the basis d, it's 0, 3, 1. This one, f3 in the basis d, it's -3, 0, 2. So we're gonna put these vectors, use them here. So 2, -1, 1, 0, 3, 1, -3, 0, 2. So that gives me the change of coordinates from F to D. They give us X in the basis F 1, -2, 2, right? From here, 1, -2, 2. And we need to find the components of X in the basis D. How we do this? To do that, one thing we learned today is we can take the matrix from F to D that we found and multiply it by X in the basis F by the theorem above. And here, what is this? This one we found it 2, -1, 1, 0, 3, 1, -3, 0, 2, and you multiply this by 1, -2, 2. And I'm sure everyone knows how to multiply this out row by column. So this row by this column, you get 2 plus 0 minus 6, that's a -4. Then this row by that column, -1 minus 6 plus 0, that's a -7. The last row by the same column, 1 minus 2 plus 4, that's a 3. So that would be the answer. Another example. In P2, second degree polynomial, find the change of coordinates matrix from the basis B. One minus 3t squared, 2 plus t minus 5t squared, 1 plus 2t, 2 to the standard basis. Then write t squared as a linear combination of the polynomials in B. So to the standard basis, what standard basis of P2? Call it C, and we know what it is. It's 1t squared. That's the standard basis for B2. So they want us to find the matrix from B to C. Again, how to do this? We start with, so since it's to C, so C goes outside. So it's going to be B1, C, B2, C, B3, C. So if we have C here to C, the outside is C, inside B. And how do you do this? Very easy. B to C. Watch how we find this. We go for the first one, B1C. What is B1C? Well, we go back to what we have here. We have 1 minus 3t squared. The 1 minus t squared, you can write 1 plus 0t minus 3t squared. So we have 1, 0, negative 3. 1, 0, negative 3. The next one is 2 plus this one, 2 plus t minus 5t squared. So 2, 1, negative 5. And the last one, it's 1, 2t. So 1, 2, no t squared. That's the change. So that's the change of the coordinates. Very easy. Then they want us to write t squared as a linear combination. So what they want us to write is C1b1 plus C2b2 plus C3b3. To start, we let x equals t squared. That's the one we're trying to write for. Or 0 plus 0t plus 0t squared. Now, x in the basis c is 0, 0, 1 from here. Then, what's next? We take B, the matrix B from B to C. Oh, notice this should be 1t squared. So what I'm trying to do here, I'm trying to find x in the basis B. What is x in the base B? Because they said write it as a linear combination of the vectors in B. That's what I need to find. Right? That's what I want to find. So we take this multiplied by x in the basis B. That gives me x in the basis C, which we know it's 0, 0, 1. This one was found. We know it. We know it's 1, 0, negative 3, 2, 1, negative 5, 1, 2, let me see, 1, 2, 0. And we have 0, 0, 1 for the other one. And we can do row reduction on this to clean up the first column. For example, you multiply row 1 by 3 added to row 3. And then you can use this one to clean up the other ones. So that will give us 1, 0, 0, 0, 1, 0, and I got 0, 0, 1. And here 3, negative 2, 1. That's what I got. So those numbers that I got here are the C's, C1, C2, C1, C2, C3. So then x components in the basis B, 3, negative 2, 1. And how does that help us? Then we can write t squared. Remember, we need to write it as a linear combinations, right? Linear combination, the basis B. So remember what we had before. I think it was 1 minus 3t squared, comma 2 plus t minus 5t squared, comma 1 plus 2t. So I take the 3 multiply by the first one minus 2 times the second one plus 1 times the third one. That's how we write t squared as a linear combination. If you multiply everything on the right side, you should get t squared. So again, b was given here, as you see. The basis b is this. To find the linear combination, or to write any polynomial as linear combinations of these, you want to take that polynomial they're asking us for, call it p of t, and you want to find c1 times 1 minus 3t squared plus c2 times 2 plus t minus 5t squared plus c3 times 1 plus 2t. But in order to get c1, c2, c3, we need to find the components of x in the basis b, which we call them c1, c2, c3. And how to do so? We need to write this as take the b to c times xb, and then use the 0, 0, 1, and to clean up, to turn this to an identity matrix, and whatever you have here, that's going to be the components of the vector x in the basis b, and those will be the c1, c2, c3. I'm looking forward to write it this way.